Okay, so in this video, we're going to tackle an optimization task. And so we've got a problem here. And the problem is we need to design a new pop can. Now, we want the largest volume cylinder from 80 pi centimeters squared of aluminum. Now, 80 pi centimeters squared of aluminum might seem like a weird number. That number is just like that, so that way we don't have to use a calculator for very much of this. But if we kind of try and think about like what is 80 pi? Well, that's a little bit more than 80 times 3.14, because it's a little bit larger than that. Now, 80 times 3.14 is a little bit larger than, so we know 80 pi is going to be greater than that, which is going to be greater than about, let's go with 240 for a minimum, which is a region that would be about 15 centimeters by 15 centimeters of aluminum. So we're talking about a pretty small can here at this point. But we're making a new can and we want the maximum volume from it. So 80 pi is a reasonable amount of material. It just also happens to work out to give us nice values. Now, we have another restriction though. The restriction is that the radius must be between 2 and 5 centimeters. Now, this restriction is because if your radius was 1 centimeter, then that would mean that your diameter of your pop can is going to be 2 centimeters, and you're going to have a very small pop can. I mean, that's like the thickness of my finger, so 2 centimeters is probably more like that. But still, it's quite a small pop can. Now, if this is the radius, 2 centimeters, then that means that my diameter would be 4 centimeters, and I can now almost hold this pop can in my hand. It would just be very tiny. So that's the minimum. And then the maximum is the radius going to 5 centimeters. And so if the radius went to 5 centimeters, which would be somewhere around here, we'd be dealing with a diameter of about 10 centimeters. And so that would be quite a large pop can, probably a little bit larger than a regular pop can. So we have these reasonable restrictions, so that way I think the pop can will fit nicely in one can. Right. Now that we've kind of gone over our restrictions, we're going to go ahead and design this pop can. Because we want to have the largest volume, I know that this is an optimization task. And it's in fact the volume that I'm going to optimize. So I'll start off by writing out the volume formula. So volume of a cylinder is pi r squared times height. Now the problem is I don't want to have two variables. If I'm optimizing, I want to optimize one variable with respect to another, because I know eventually I'm going to need the rate of change of the volume with respect to some other variable. So I'll have to pick one. So it'd be really nice if I had either my height in terms of my radius or my radius in terms of my height. For that, I'm going to use my constraint. That's the other formula. So not only is there volume of a surface area, but there's also, volume of a cylinder. I kind of gave away the hint. There's also surface area of a cylinder. And so the surface area is 2 pi r squared plus 2 pi r h. And because we were given a particular amount of material, we know the maximum surface area is going to be 80 pi. So we can substitute that in, and we'll be able to rearrange this equation, to solve for h in terms of r. So it looks like each term contains a pi, so I'm going to cancel those. It looks like each term contains a 2, so I'm going to divide everything by 2. So that will leave me with 40 is equal to r squared plus plus rh. Should have used pen here. So that's r squared plus rh. Now, I want h alone, so I'm going to subtract r squared from both sides and divide both sides by r. So this will be 40 over r minus r squared is equal to h. Now, I could leave this expression like this, but I know the derivative of powers. I know the power rule. I don't yet have the quotient rule defined, so it would be much easier if I didn't have this in a form that doesn't look like standard form. So I'm going to decompose this fraction. So what that means is this r is going to divide into both the 40 and into the r squared. So in decomposing this fraction, I'll have 40 over r minus r is equal to h. Fantastic. So that means I can go back into my volume formula and rewrite my value of h. So my volume formula was v equals pi r squared times h. So that's now pi r squared times, and my new h is 40 over r minus r. We'll just go ahead and do a quick expansion. So we'll expand this pi r squared into each of these terms. And that's going to give me a nice looking polynomial. So it'll be about 40 pi r, because this r will cancel with one of these. Pardon me. Minus pi r cubed. Because multiply powers, we increase the exponent. So I now have an expression of volume with only r as a variable. That's fantastic, because in an optimization task, my first thing I need to do is provide myself with a function. The second thing I need to do is provide myself with some boundaries, and I have my boundaries here. Here I know that r is between 2 and 5. And the last thing I need to do is search to see if there's any extrema within those boundaries. So I search for extrema by trying to find the derivative and setting it equal to 0. So I'm going to find the derivative of volume with respect to r. Now, I just use the power rule, so the exponent is 1, so I have 40 times pi times 1, or 40 pi. And this will be minus 3 pi r squared. Rather easy derivative to take. Now, because I'm looking for extrema, I'm going to set dv dr equal to 0. So that would mean I'll have 0 is equal to 40 pi minus 3 pi r squared. And I'll solve for r. So I think what I'm going to do is I'm just going to move 3 pi r over to the other side. So this is going to be 3 pi r squared is equal to 40 pi. I notice both terms have pi's, so I'll cancel those out. Gone, gone. I'll divide both sides by 3. So I'll have r squared is equal to 40 over 3. And I'll take the square root. And so when taking the square root, I know that I'm going to have both a positive and a negative. So the square root of 40 is 2 root 10. And the square root of 3 is the square root of 3. Let's put that over the square root of 3. Now I could get fancy and rationalize my denominator. I don't really need to, though. I just need to do a few little quick calculations here. First off, one of the quick calculations is I have 2 critical values. So this means there's 2 extrema. And if I look at this, this is a cubic, and it's a negative cubic. So a quick sketch of this negative cubic is going to tell me that its end behaviors start up there and end down here, and it has 2 critical values. Really importantly about these critical values is they're the same magnitude, but one's positive and one's negative. So there's probably one over here at some height, and then there's probably one over here at some other height. And I'm kind of guessing that this is a minimum first because it's coming down. And it's going to go through 0 because when the radius is 0, we fully expect this volume to be 0. I'll come back up and reach that maximum and come back down. So I think that this maximum is the thing that we want. That's the maximum value of r. Now our hope is that 2 happens before that maximum and 5 happens after that maximum. So we just have to verify that this number is in between 2 and 5. Well, a quick calculation. The square root of 10 and the square root of 3. Square root of 10 is a little bit bigger than 3. So, because it's a little bit bigger than 9, right? So we just have something a little bit bigger than 3 divided by the square root of 3. So I think this is going to be a little bit bigger than the square root of 3. Now the square root of 3 is 1.73 something, something, something. So I'll bring back my approximate sheet here. 2 root 10 over root 3. All right, so I have a feeling that this thing is going to be less than 2 root 12 root 3. The reason why I think it's going to be less than that is because of the fact that it's, 2 root 12 root 3 is going to be a bigger number than this. Now, why did I pick 12? Well, I picked 12 because I can take this root 3 and divide it in. Root of 12 divided by root of 3 is the root of 4. So that means 2 root 10 root 3 is less than 2 root 4. Of course, 2 root 4 is 4, because the square root of 4 is 2, and 2 times 2 is 4. So I know 2 root 10 root 3 is less than 4. Now, I also know that this is going to be greater than 2 root, let's go root 9 over root 3. And I'm just kind of giving myself a reasonable estimate for this number to verify that it's on the boundary between 2 and 5. Also, I know that 4 is less than 5. So far I know, okay, well, 5 is here and 2 is here. Then so far I know that at least this number is less than 5. And now I just want to check that it's greater than 2. So here's a number just less than 2 root 10 over root 3. And so that's going to be 2 root 3. And 2 root 3 is 2 times, and this just happens to be a radical that I know. It's about 1.73 something. And 1.73 times 2 is about 3.5 something. So this is approximately equal to, let's go 3.46. So I know that my answer is in between 4 and 3.46. So yes, it is in between 2 and 5. So this is going to be a valid thing for me to go ahead and check, which means that my maximum definitely exists between 2 and 5. Cool. Now that I know that, I just need to check to see whether or not it actually is a maximum. Because remember, I know that it is based off of this graph, but what if I didn't know what the graph of a cubic looked like? Well, I suppose then I'd have to show that this particular value of 2 root 10 over root 3 is going to be a maximum. And the way that I can do that is with the second derivative test. So buckle up, we're going to take the second derivative. So the second derivative of volume with respect to the radius is equal to, now the derivative of 40 pi is 0, so then I have minus 6 pi r. Okay, so now remember the second derivative test says, if you take the second derivative, and we'll just simplify this up a little bit, negative 6 pi r. If you take the second derivative and substitute in your value and you end up with a negative, then that means that you're dealing with a maximum. If you substitute it in and you end up with a positive, then that means you're dealing with a minimum. Now, let's see what would happen to the value of the second derivative at this point. Remember, there's 2 points here, right? But we're going to ignore the negative one. And the reason why we're going to ignore it is because it's obviously not between 2 and 5. But let's take a look at where the negative 1 would end up over here. So the negative 1 would be there. And we suspect that that's a minimum. Well, if I evaluate the second derivative of volume with respect to the radius, at that point, it's going to be negative 6 times pi times negative 2 root 10 over root 3. Well, a negative times a negative is a positive. So that means the second derivative is greater than 0, which indicates that we're dealing with a graph that's concave up. And because it's concave up, it's going to contain a minimum. So by the second derivative test, we know that this one is going to be a minimum. It's for that same reason that I can say that the second derivative of the radius at a value of r is equal to 2 root 10 over root 3 is going to be equal to negative 6 times pi times 2 root 10 over root 3. Now, I don't really care what that is. I just care that it's going to be less than 0. So we have a minimum. Sorry, a maximum. So that means I've got a local maximum at that particular point. And I just need to make sure that that local maximum is not beaten out by any others. Now, I do know that there's only 2 zeros, so there's only 2 critical values. So at this point, I'm pretty sure that this is the answer. But I should check the boundaries just to make absolute sure, especially if I didn't have a picture of this graph or if I didn't have the second derivative test. So the graph told me I was done right here, and the second derivative test told me that I was done right here. But let's take a look at another way. So now that we know our value of r, again, we're just going to disregard the negative here. We're going to test the volume for a few different radiuses. So the volume for radius equals 2. So this is going to be, we'll go to 40 pi times 2 minus pi times 2 cubed. So this is going to be 80 pi minus 8 pi, or 72 pi. And we'll check the volume for a radius equal to 5. Just checking my boundaries here to verify that these points are in fact lower than this point. So I'll have 40 times pi times 5 minus pi times 5 cubed. So this is going to be 200 pi minus 125 pi, or 75 pi. So these are actually relatively close. Seems like my boundary is almost symmetrical about my extrema. Now I'll check my extrema. Value of r equal to 2 root 10 over root 3. So this is going to be 40 times pi times 2 root 10 over root 3 minus, this is going to be pi times 2 root 10 over root 3 cubed. Okay. Well, this is 80 root 10 over root 3. So again, root 10 over root 3 was about 1.73. So this is going to be about 160 pi. And this is going to be 8 times 10 root 10. So 80 root 10 divided by 3 root 3. So about 27 root 10 over 3 times pi. Ugh, this is ugly. Oh, well, we've got 80 root 10 over 3, root 3 times pi, minus 27. So that's going to be about, it's not going to be, ugly number here. I think I'm going to go and grab a calculator. Just give me a second here. I should play some calculator music over top of this. That's annoying, isn't it? Pi times. All right, well, that works out to 305.91. And for those of you who are interested, 305.91 divided by pi is roughly equal to about 97.5 pi. So I'll just go 97 pi. It's actually a little bit greater than 97 pi. So because this is obviously greater than these, we're clearly dealing with a maximum at that particular radius. So the last thing to do would be to substitute our radius back into our formula up here and solve for our height. Well, may as well go ahead and do that. We're already here. So remember our formula that connected the radius and the height was 40 over r minus r is equal to h. that was the easiest version of our formula that we had here. So that was the simplest version of our formula we ever had for h. So this is 40 over 2 root 10. And it's because it's over 2 root 10 root 3, I'm just going to write the root 3 up here, minus 2 root 10 over root 3. Well, 40 becomes 20. Now, 20 is 2 times 10, which is 2 times the root of 10 times the root of 10 times the root of 3 minus 2 root 10 over root 3. So I think that I can actually cancel out one of the root 10s. So that's gone. So I've got 2 root 10 root 3 minus 2 root 10. Seems like I can factor something there. 2 root 10 is going to factor out. That'll leave me with root 3 minus 1 over root 3 is equal to my height. And I could probably rationalize that, make it work a little bit nicer and come up with an easier value. But really, I mean, I should have just substituted these values into my calculator here and come up with an expression for the height of my pop can at that particular point. But I've now designed my pop can. So my pop can has a radius of 2 root 10 root 3, a height of 2 root 10 root 3 minus 1 over root 3, and a volume of about 97 pi, or 305.91 centimeters squared. Cool.